Every modern AI model has a trick that lets it read an entire sentence all at once. Forwards, backwards, sideways, and somewhere in that process it's forced to go completely blind on purpose. I'm Kuro, and today we're cracking that mechanism open, starting with one deceptively simple sentence: the cat sat on the mat because it was tired. How does AI know it means the cat, not the mat? That trick is called attention, and it quietly rebuilt every model you ever talked to, blind spot included. Before attention, models read text the way you'd read, with a finger under each word. One word at a time, carrying everything so far in a single running summary. By the time it reached it, 20 words later, the memory of cat had already faded, and fading memory turns out to be the smaller of its two problems. These were recurrent neural networks, RNNs, and they had two real problems. First, everything got squeezed into one fixed size memory slot, so old detail kept getting overwritten. Second, word 10 literally couldn't be processed until word 9 finished. No shortcuts, no parallel work, and no obvious fix in sight. If reading one word at a time is a bottleneck, what would you let the model do instead? Take a guess. The real answer is simpler than you'd expect. What if a word didn't need a relay race of memory at all? What if every single word could just look directly at every other word, all at once? That's the entire idea. No summary, no relay, just direct connections. It's called self-retention, but look at every word. Raises an obvious question. Look at them how? Exactly. Picture every word in the sentence as a person sitting at a round table. Each person holds up two cards, a question they are asking and a description of what they offer. It holds up a card asking, "Who am I referring to?" and scans the table for the best match. Those cards have real names and they're about to get less metaphorical. Here are the real names behind those two cards, query and key. Every word gets three learned vectors from its embedding, a query, a key, and a value. Its query gets dot producted against every other word's key. That score measures relevance. Those scores get run through softmax to become weights, then used to blend every word's value together, on paper anyway. What does that actually look like for our sentence? Run the actual math, and this is what comes out for our sentence. It ends up with a heavy weight on cat and barely any weight on mat. Not because of a rule someone wrote, because training shaped the query and key vectors to line up that way, all by chasing one single relationship at a time. One attention pass finds only kind of relationship. What if a sentence has several going on at once? Grammar, meaning, position, comment which one you think matters most. Turns out you don't have to pick just one. Here's the real fix. Don't run attention once, run it several times in parallel, called multiple heads. The original paper used 8 of them, each with its own learned query, key, and value weights. One head might lack grammar, another co-reference like it, another just word order, and none of them know what position anything is in yet. Here's a gap in the mechanism nobody mentions until it bites you. Comparing every word to every other word treats the sentence like a bag of words. Order is gone. So before any of this runs, a positional encoding gets added, marking each word spot in line. A neat fix, but it doesn't touch the mechanism's bigger, costlier problem. Now the honest limitation, because compare every word to every other word, has a real cost. Double the sentence length, and the comparisons don't double. They roughly quadruple. That's O(n) squared. The exact same quadratic wall we've hit talking about context windows before, and it's expensive enough that entire research teams exist just to dodge it. This is where FlashAttention comes in, not a shortcut on the math, a smarter way to compute the same math. It fuses the steps, so the huge intermediate score grid never gets fully written out to slow memory. FlashAttention 3 from Pridehouse team layers on async execution and low precision math for another real speed up. Though squeezing the same math faster isn't the only way to attack this problem. There's a second approach that just changes what gets compared at all. Sliding window attention only lets each word look at a fixed nearby range, not the whole sequence. Mistraw's models popularized this. It trades a little long-range awareness for real linear scaling speed, but a little is doing a lot of work in that sentence. If sliding window attention can't see far back words directly, how might information still travel that far? Hint: stacking is involved. What's your guess? Attention is only half of one transformer block. Here's the full real shape. After self-attention runs, its output gets added back to the input, then normalized, a residual connection. That feeds into a small feed-forward layer, then another add and normalize step. That whole unit is one transformer block, and real models stack dozens of them. How many, and why does stacking even matter? This answers the earlier question: how information travels past a narrow window. The original paper stacked 6 blocks. Modern large models stack 80, 100, sometimes more. Each layer up, information from further away gets folded in a little more. Depth does what one window can't. But stacking blocks assumes you even know what shape those blocks should take. The original 2017 transformer actually had two halves, an encoder and a decoder, built for translation. Encoder-only models like BERT kept just the reading half, great at understanding, not writing. Decoder. Only models like GPT kept just the writing half, and that shape hides a strict rule about what it's allowed to look at while writing. If a decoder is generating word by word, should it be allowed to peek at words that come after the one it's writing? Think about it before the next chapter answers it. This is that blind spot Kuro teased back in the hook, and the trick behind it is stricter than you'd guess. The short answer is no, and it's enforced with a real technique called Causal Masking. Before softmax runs, every score pointing to a future word gets set to negative infinity. Softmax turns that into a weight of exactly 0. The future is mathematically invisible every single step, but blocking future words isn't the only boundary attention respects on purpose. People mix up two closely related terms, so let's separate them cleanly. Self-attention, a sequence comparing its own words against each other, everything we've covered so far. Cross-attention, the decoder's queries reach into the encoder's keys and values instead of its own. Translation models use exactly this, the English decoder cross-attending into the French encoder's output, and that translation paper is exactly where this entire mechanism was first proven. This isn't a hypothetical mechanism, it's one specific 2017 paper. Attention is all you need. 8 researchers at Google Brain and Google Research published it, almost as a side project. BERT, GPT, T5, and even the vision transformer for images all descend from that same block, which raises an uncomfortable question about how long any one architecture stays on top. Given how expensive quadratic attention gets, do you think it will still be the dominant architecture in 5 years? Real disagreement exists on this one. Argue it out below. Attention isn't the only serious approach left standing anymore either. Mamba, a state space model from late 2002-3, processes sequences in linear time instead of quadratic. It's not replacing attention in most production models yet, but it's a real active research direction, and it's not the only assumption about attention worth questioning. One myth Kuro needs to squash before we wrap up. Attention means the model understands what it's reading. It doesn't, not in any conscious sense. It's a learned weighted average, nothing more mystical than that, just a very well tuned one. So, what's actually left once you strip away the metaphors? Let's fold this whole episode back together. The problem: RNNs read one word at a time and quietly forgot long range detail. The mechanism, query, key, and value vectors let every word directly compare itself to every other word. The trade-off, quadratic cost, fought back with FlashAttention and sliding windows. That's attention, not magic, just every word getting to ask every other word one very good question. Next time, another piece of the machine actually running under your favorite AI tool. Did it finally make sense? Tell Kuro below and subscribe for the next one.